Hey guys, so welcome back to Segui tutorial channel, and ang pag-uusapan natin ngayon is another problem for flexural strength, which is our problem number 5 for non-compact shape. A simply supported beam with a span length of 13.7 meters is laterally supported at its ends and is subjected to the following service loads. That load is equivalent to 5.84 kN per meter, which this load includes the weight of the beam, and live load is equivalent to 1.46 kN per meter. If Fy is equivalent to 345 megapascal, is a W14 by 90 adequate? Okay, so kapares lang dito ng ating problem number 3. Okay, so i-check natin yung yung capacity or strength ng ating beam dun sa loadings na kanyang dadalhin. So, this is a simply supported beam na kung saan ang kanyang lateral support is nasa ends. Okay, so ibig sabihin, yung kanyang unbraced length is yung mismong 13.7 meters. Okay? Then, nakanote naman dito yung dead load, kasama na raw dun yung weight ng beam natin. Hindi natin kailangan gawin yung ginawa natin sa ating problem number 3 na kung saan sunod pa natin yung load. Ayan, ito. Okay? Then, ayan, so pwede na tayo mag-start. Pero before that, we must check the shape classification ng ating beam. Check, pwede natin sabihin na local stability, kagaya ng ginagawa natin sa compression members. Okay? So, solve natin yung ating lambda. And yung ating B over 2PF. Ang ating B dito is 359, no? So, 359 then over 2 multiplied by TF. Ang ating thickness is 18. So, this is 9.972. And then, check natin yung ating lambda P and lambda R. So, ito yung ating table B 4.1B. Para sa width to thickness ratios, so ito yung ating lambda P and lambda R, so 0.38 and 1.0. So this is 0.38 square root of E over Fy, and this is equivalent to 1.0 square root of E over Fy. So 0.38 multiplied by 200,000 over Fy is equivalent to 345. Oops, sorry. This is... ano pala? Oops. Ayan. Okay. So, 9.15. Okay, then, patan ito ng 1.0. So, 24.08. So, ngayon, yung ating lambda is greater than sa ating lambda P, but less than sa ating lambda R. So, anong indication nun? So, check natin dito sa ating table. Ang nakalagay kasi rito, yung ating lambda P, ito yung nag-determine kung compact or non-compact yung ating section, hindi ba? So, sa ating problem number 3 and number 4, yung ating lambda kasi is nag-less than sa ating lambda P. Okay, so ibig sabihin, non-compact tayo. Pero once na nag-greater than tayo sa ating lambda P, ibig sabihin, non-compact section na yung ating beam. Pero magiging non-compact lang siya kung less than naman siya sa ating lambda R. Kaya nga nakalagay sa lambda R, it is non-compact or slender. Kasi dito natin matutukoy kung non-compact or slender yung ating section. So, since nag-greater than tayo sa ating nag-greater than tayo sa ating lambda P, but less than tayo sa lambda R, ibig sabihin, non-compact yung ating section. Yun yung ibig sabihin ng compact or non-compact, and non-compact or slender, which is, I believe, na na-discuss rin namin nung introduction. Okay, so nire-remind lang namin. Ayan. So, ngayon, mau-conclude natin na yung ating section is a non-compact shape. Ayan. Okay. So, since non-compact yan, dito tayo papasok. So, if the sheet is non-compact because of the flange, actually, hindi natin kailangan pang i-check yung sa height niya eh. Kasi sinabi namin sa introduction na once na ang isa sa kanila is nagkaroon ng, or once ang isa sa kanila, flange man or web is naging non-compact, ibig sabihin yung buong section natin is ititreat natin as non-compact section. Okay? So, the nominal strength will be the smaller of the strength corresponding to flange, local backlink, and lateral torsional backlink. So, nasaan yung ating flange local backlink? Ito. And ito yung ating lateral torsional backlink. So, ibig sabihin, dalawa yung isosolve natin na strength. So, check muna dito sa flange local backlink. So, letter A muna tayo. Punta tayo para sa ating flange local backlink. So, sabi rito, since doon tayo sa second condition, if lambda is greater than lambda p but less than to lambda r, the flange is non-compact, and ito yung ating mn. Okay? So, ang mn natin is mp minus 0.7 fy sx, then multiplied by, okay, so, sana na-memorize natin. Okay? So, ang ating mn is equivalent to mp minus minus 0.7 of fy multiplied by sx multiplied by lambda minus lambda p over lambda lambda minus lambda r. Balik na data. Sorry. This is lambda p. Ayan. Minus lambda r. Or sorry. It is lambda r kasi mas malaki yung lambda r ne. Okay? Ayan. So, check natin. Ayan. So, lambda r minus lambda p. Okay, so, ulitin lang natin itong ating point, yung ating FYSX, this is our yield moment, na kung saan, sa yield moment natin, binawasan natin ng 30% yung ating FY. Kaya merong 0.7 yan. Okay? So, solve natin yung ating MP. Ang ating MP is equivalent to FY multiplied by plastic section modulus. So, given naman yung ating plastic section modulus, that is 2.57 times 10 raised to 6 multiplied by Fy, which is 345. So, i-divide natin ng 1,000 squared para maging kilonewton meter. So, 886.65. And this is kilonewton meter. Pero, syempre, kapag sinubstitute natin dito yan, kasi ang makuha natin dito is newton millimeter. So, kailangan natin i-convert itong 886.65 ng Newton millimeter. Okay? Meron naman tayong lambda. Okay, kompleto naman na. So, masasolve natin yung ating mn under sa flange local backlink. So, ang mp natin is 886.65 times 10 raised to 6 minus mp 886.65 times 10 raised to 6 minus 0.7 of fy 345 multiplied by sx. Okay, so hindi pa natin nasasolve ang sx, no? Ang sx natin is ix over c. So, dito na lang. Ix over c. Ang ating c dito is yung kalahati ng 356 since double symmetrical naman siya. So, 356 over 2. And then, ix is 415.82 times 10 raised to 6 over the answer. So, this is 2.336. 2.336 or siguro dito na lang. Ayan. 2.336 times 10 raised to 6 millimeter cube. Okay. So, balik natin yung kanina. Ayan. So, 345 multiplied by 2.336 times 10 raised to 6. Okay, multiplied by lambda. Ang ating lambda is 9.972 minus lambda p, which is 9.15, over lambda r, which is 24.08 minus 9.15. And then, divide natin ng 1,000 squared para maging kilonewton meter. So, 868.894. Okay. So, 868.894. kilo Newton meter. So, shade natin. So, ito yung ating MN1 or yung ating nominal moment for the flange local buckling condition. And then, solve natin yung ating sa letter B para sa ano ba nakalagay ron? Okay, sa lateral torsional buckling. So, para dito, kailangan nating i-check yung ating unbraced length kung siya ba ay greater than sa LP or less than sa LR. So, ang ating LB is 13.7. So, solve natin yung LP. Equation natin para sa LP. Okay, wala rito. So, siguro i-copy na lang natin nasa problem number 3 or 4. Okay, yan. So, ito yung para sa LP. So, dito, ang ating LP is equivalent to 1.76. Okay, so susub ulit natin yung ating RY. So, ito na lang. Ang ating RY is equivalent to square root of IY 150.68 times 10 raised to 6. Okay. Over area 17096.74. So, RY natin is 93.88. Tama ba? Okay. 88 millimeters. So, this is 1.76. Oops, sorry. 1.76 multiplied by RY, 93.88, multiplied by the square root of 200,000 over FY. So, 3978, divide natin ng 1,000 para maging meters. So, 3.98. So, 3.98 meters. And then, solve natin yung LR. Yung napakahabang equation para sa LR natin. Yan. Dito na lang siguro. At hindi na rin naman kasya dito, no? Okay na yan. Then, lagyan lang natin ito yung value ng LR. Okay, meron tayong RTS. Given naman. Meron tayong okay, JNC. Okay, so since ito naman is, wide flange, ang ating C is equivalent to 1.0. Okay, SX, meron na. H sub O, okay. Ayan. So, ang gawin natin, ito is, wait lang. Okay, so gawin natin, ito yung ating alpha A. Ito naman, yung nasa loob, is gawin natin alpha B. Okay. So, E natin, 200,000 over 0.7 of FY, 345. So, alpha A. And then, JC, 1.69 times 10 raised to 6 multiplied by C over SX, which is 2.336 times 10 raised to 6 multiplied by H sub O na 337.82. Yan. So, ito yung ating alpha B. Okay, so masasabi natin yung ating LR, 1.95 RTS, 104.4 multiplied by E over 0.7 FY. Wait lang, check nga natin yung kanina. Okay, so tama naman, no? So, 1.97 times 104.4 times E, which is our alpha A, no? Ayan. Then, the square root of alpha B multiplied by the square root of 1 plus square root of 1 plus 6. 76. 76 multiplied by, okay, ito kasi reciprocal to nung letter A natin hindi ba? So, gagawin natin 1 over A. 1 over A. And then, okay, so nasa loob, no? Then, yung ating SX issue over GC is reciprocal ng ating alpha B. So, multiplied by 1 over B. Then, square. Ayan. So, 12.996. So, divide natin na 1,000 para maging meter. So, ano siya? Estimate natin 13 meters na siya. So, ang ating LR is 13 meters. Ayan. So, ngayon, yung ating LB, since ang ating LB is greater than sa LR, therefore, dito tayo papasok. Yan. There is elastic lateral torsional buckling. So, elastic LTB or lateral torsional buckling. So, ngayon, ang ating MN is equivalent to our critical buckling stress na FCR multiplied by SX na kung saan dapat less than or ano siya or equal to MP. Yan. So, solve natin yung FCR natin. Ito yung equation. So, FCR is equivalent to CB pi squared E over LB over RTS squared multiplied by the square root of 1 plus 0.0 1 plus 0.078 multiplied by JC over JC over SX is sub O multiplied by LB over RTS squared. Tama ba? Check natin. Okay. So, meron na tayo nito. Yung LB over RTS na lang, gawin natin siya as alpha C. Kasi, dalawang beses natin siyang gagamitin. So, ang ating LB is 13 meters, no? Okay, so ang ating LB is 13,000, no? Kasi 13 meters. Sorry. This is 13.7 pala. 13.7, no? Times 10 raised to 3 para maging 13,700 para maging millimeters. Then, ang RTS natin is 104.4. Then, square natin yan. So, ito na yung ating LB over RTS squared. Yan. So, na-store natin sa C. Then, ano ang CB? Okay, so since this is simply supported beam, tapos uniformly distributed load yung ating dadalhin, so, i-check natin sa introduction natin, ang CB natin dapat is 1.40. Okay? So, CB should be equivalent to 1.14. So, sabi natin, 1.14 multiplied by pi squared over 200,000 over LB RT squared, that is alpha C, then multiplied by, square root of 1 plus 0.078 multiplied by JC, that is alpha B. Then multiplied by LB over RTS squared, that is alpha C. And so 257.28. Ang ating FCR is equivalent to 257. Tama ba? 257.28 mega Pascal. So, masasabi natin ngayon ang ating MN. Ang ating MN is FCR na 257.28 multiplied by SX, which is equivalent to 2.336 times 10 raised to 6. Okay? Then, divided by 1,000 squared. So, 601.00 kilo Newton meter. Okay, actually, it is 0.01. Yan. Kilo Newton meter. Okay, so double check natin to, no? So, tama lang, no? ZX, no? Yan. So, ngayon, meron na tayong MN under sa lateral torsional buckling. So, mamimili tayo ngayon sa dalawa. So, since mas maliit itong sa lateral torsional buckling, ito yung mag-govern para maging safe yung ating beam. So, therefore, ang ating MN is equivalent to, or the nominal bending strength or bending capacity of our section is 601.01 kilonewton. So, ngayon, i-check natin kung adequate ba ang ating section. So, kaparehas lang sa ating problem number 3, pero included na yung ating weight sa dead load. So ngayon, solve na lang natin yung ating WU. Ang ating WU is WDL plus 1.6 of WLL. So 1.2 of 5.84 plus 1.6 multiplied by 1.46. So this is 9.334. So 334 ba? 344 pala, sorry. 9.344 kilonewton per meter. So therefore, ang ating MU is WU L squared over 8. So 9.34 at 344 multiplied by L, which is 13.7 squared over 8. So this is 219.222 kilo Newton meter. So ngayon, i-compare natin yung ating MU sa ating design strength. So ating design moment capacity or design moment strength is okay, 0.90. 0.90 of 601.01. So 540.91 kilo Newton meter. So since ang ating MU is less than sa ating design strength, therefore, yung ating beam is adequate. Yeah. Okay, so ito yung ating final conclusion and answer. Ayan, so napakasimple lang, di ba? Ang ang pinagkaiba lang kasi nila sa compact is ang ginamit natin dito is flange local backlink and lateral torsional backlink. Kasi kapag compact, nakafocus lang tayo sa okay, sa lateral torsional backlink. Ayan. Dito lang yung focus natin. Okay, kapag compact section. Pero, kapag non-compact section na kasi, magkakaroon tayo ng another or kukuha tayo ng another strength from another condition ng ating beam. Which is, since non-compact nga siya, possible kasi na mag-fail yung ating local or yung ating element sa ating section. Kaya kailangan natin i-check yung strength niya in terms of local, in terms of flange local backlink. Kaya nakapag-solve tayo ng MN under dun sa condition na yun. And then, syempre, hindi natin pwedeng palagpasin yung strength ng ating beam in terms of lateral torsional backlink. Kasi yung lateral torsional backlink, ito yung overall backlink. So, kailangan natin siyang i-check parehas. Okay? Yun yung pinagkaiba lang naman ng non-compact sa compact. Pero, parehas na parehas pa rin naman. Madali lang naman din siyang diba, i-analyze. As long as sundin lang natin yung ating code, wala tayong magiging problema. Compact man yan or non-compact section. Okay? So, ayan. So, tapos na yung ating 5 problems under sa ating flexural strength ng chapter 5 of steel design. And tutok lang kayo sa Segui tutorial channel kasi patuloy lamang kami na mag-upload ng mga video tutorials sa steel design and iba pang mga subjects na possible na magawa namin ng paraan at oras upang magawa. Okay, so thank you for watching and see you next time on our channel. Okay, so bye-bye!